Where do you see yourself in 10 years? We understand the impact your academic...
So in this video, I'm going to derive the two versions of Young's double slit formula for the distance between maximums. The top formula gives an angular separation, and the bottom one gives a distance, s. To first establish the conditions when this happens, we'll say that coherent light of the same amplitude goes through two slits. Light diffracts through both of those slits, and then interferes with itself on the other side of the slits. This has been shown experimentally to produce a pattern on a screen in which the intensity of the light oscillates from 0 to some maximum, which is the graph I'm showing in the diagram. So, how can this be explained theoretically? It begins by simplifying the situation. We don't need to focus on all of the light at once, but just the beams that happen to land on the same spot on the screen. Let's first consider two beams of light that travel to the center of the screen. From the symmetry of the situation, maybe you can see that the distance that the two beams travel is exactly the same. Since the light had a constant phase difference, initially, we can leverage the principle of superposition to see that the waves will constructively interfere, since they're perfectly lined up. Hence, it is quite clear that the center of the screen should be a maximum. So we'll be able to label that n equals 0, because it's essentially a trivial maximum, and as you'll see in a moment, that's helpful for the derivation as well. Now let's consider how the first maximum, n equals 1, is possible. In order for constructive interference to occur, the waves have to be in phase. The troughs and the peaks have to line up, right? But that can happen even if the other wave travels a full wavelength longer. In fact, the waves would be in phase even if the other traveled 2 or 3 or 4 wavelengths longer. As you can hopefully see in the diagram, the peaks and the troughs totally line up even when there's this path difference of 1 wavelength. In general, if the path difference is an integer number of wavelengths, constructive interference occurs. Returning to our diagram, that means that L2 must be an integer number of wavelengths longer than L1. In this case, it's just 1 wavelength longer, but I'm trying to keep this as general as possible to apply to all maximums. So we're going to keep it as n lambda. So now the question becomes, how do we know when the path difference will be an integer number of wavelengths? Unfortunately, this is where we need to make some use of the geometry of the situation and some valid approximations. Often the approximations are the hardest part to understand, so we'll work on making those clear. Okay, to find the relationship, we'll want to only use things that are available to use on this diagram and kind of in the experiment. So let's add 2 lines and assign them variables. Let lowercase d be the distance between the slits, and capital D be the distance from the slits to the screen. Finally, I'll add a line from the center of the slits to the maximum. Now, it's important to realize that this diagram is absolutely not to scale. Capital D will be much, much larger than lowercase d in any experiment you do. Normally, capital D would be hundreds of times longer than lowercase d. So maybe you can see that if capital D is really much, much larger than lowercase d, then the two beams of light and the light from the line from the center of the slits to the maximum will essentially be parallel, because they're at such tiny angles to each other in order to meet after capital D in meters. Honestly, you could treat all 3 lines as starting and ending on the same point. Not only are they parallel, but when you're zoomed out like this, for all intents and purposes, they're the same line. But to exaggerate the distance between them and show how parallel they are, let's look closer. We can then add an angle theta between capital D and the line from the slits to the maximum. Then this angle is 90 minus theta, since capital D is perpendicular to lowercase d. And then because this is a right triangle, this angle is theta. After that, using a bit of right angle trigonometry with lowercase d as the hypotenuse and n lambda as the opposite, we know that n lambda equals d sine theta, which is one of the formulas you can use. Then we can take this formula and apply a little more math to find the fringe spacing in units of meters. All we have to do is add the variable s for the fringe spacing and see that tan theta equals opposite over adjacent, or s over capital D. We can then consider that for very small angles, tan theta is approximately equal to sine theta, which you start to see in the red triangle because the hypotenuse is almost the same size as the adjacent, and sine theta is opposite over hypotenuse. Using that approximation, we can substitute our expression for tan theta into sine theta, and we find that an integer multiple of the wavelength is equal to ds over capital D. With some quick rearranging, we find that the distance from the central maximum to the nth maximum is n times the wavelength of light times the distance from the slit to the screen divided by the distance between the slits. So that's it. I hope you found it useful, and if you have any questions, ask them in the comments. Thanks for watching, and bye-bye.